what is the greatest common factor of 20 factorial and 200,000? Now, in case anybody's wondering, that 20 exclamation point doesn't mean you should say factor of 20 and 200,000. No. That 20 exclamation point just means 20 factorial, which means that number, which in this case is 20, multiplied all the way down to 1. So 20 times 19 times 18 times 17 and all the way down to 3 times 2 times 1. So after you know this, the problem should be super easy, right? Because you understand it, so it should be pretty easy. Nah, 20 factorial is still a gigantic number. So, no, not easy. And also, 200,000 is also a rather significantly large number. So, we can use a very common yet a little complicated method to do this. It's called prime factorization. And, well, first of all, what is prime factorization? And second, how does it help us solve this problem? Well, prime factorization is a number, like any number, say 16, expressed in terms of primes. Well, 16 is 2 times 2 times 2 times 2 times 2, more formally known as 2 to the 4th. So, in other words, 2 to the 4th is the prime factorization of 16. So how does prime factorization help us solve this? Let's say we had another number, 18, which is 3 times 6, while 6 is 2 times 3, so we have 3 times 3 times 2, which is 2 times 3 squared. So 2 times 3 squared is the prime factorization of 18. So, well, now to find the prime, and now to find the greatest common factor, which is what we want in our problem, well, then we can look at the common numbers, or in this case, number, which is 2, and then the lowest exponent that is in common. And here it's just 1, because if we had 2 squared, well 2 squared can go into 2 to the 4th, sure, but it can't go into 2 times 3 squared. So the greatest exponent that we can have here is just 1, so the greatest common factor is 2. I'm not going to fully circle that. So this can help us in a much more complicated problem. I'm going to go a little higher, but not this complicated. Say we had a number that whose prime factorization was 2 to the 6th times 3 to the 4th times 5 squared times 7, and let's see, 2 to the 4th times 3 cubed times 7 cubed, and then we wanted to find the greatest common factor, GCF. And that's the notation. Well, same way. Look at the common numbers, which here is 2, that's 3, 2, 3, and 7. So, well, the greatest common exponent here is 4, because 2 to the 5th can go into 2 to the 6th, but not 2 to the 4th. Well, here just 3 cubed is the greatest common exponent. 7 cubed and 7, the greatest common exponent there is 1. And of course, you can just multiply these together. Now, this 5 squared here, there's no other 5 in the other numbers, so we can just leave it there. That 5 squared doesn't do anything to us over here. So the greatest common factor of these two numbers calculates to be 2 to the 4th times 3 cubed times 7 to the 1st. So we kind of have an idea about how to do this problem of prime factorization. I'm going to erase that because we need that very precious space. So I'm going to start with finding a prime factorization of 200,000 because 20 factorial seems kind of scary. So I'm going to leave that to do later. 200,000. So for these big numbers, we don't have to keep doing trial and error until we find a prime factorization, we can use something called a factor tree, which keeps just breaking up numbers into less and less complicated numbers until you just get a whole string of primes. So you can start with 4 and 50,000. You might notice you're just dividing by 4 to get 50,000. Well, 4 is 2 times 2. There we go. That's 2 primes. Well, 50,000, I can break that up into 5 times 10,000. There we go. 5's the prime. And breaking up 10,000, which is 10 times 1,000, you can tell from its name pretty easily. Well, here 10 is 2 times 5. 2, 5 primes. It's pretty straightforward. See, 10,000 is 10 times 100. We have 10 again, which is 2 and 5. 100 is 10 and 10. Each 10 has 2 and 5. 2, 5. I'm just going to trade pens really quick. It's running out. Just outline this again. Oh yeah, much better. Okay, so now, we can just count how many 2's and 5's we have here, because that's the only thing that is in this prime factorization. We have 1, 2, 3, 4, 5, 6 2's. Just gonna write it up here. 2 to the 6th, and then 1, 2, 3, 4, 5 5's. So times 5 to the 5th. So this is the prime factorization of 200,000. And I have to finally do that scary thing. So instead of computing 20 factorial, which I would rather die than doing that, we can compute the prime factorization separately. Or in other words, well, 20 factorial is made of a whole bunch of numbers, right? 20 times 19 times all the way down. And we can compute each of these numbers separately. And that might seem like a very daunting task too, but there's 2 things that make it easier. First, well, we're only looking for 2's and 5's because, well, if we had like a 7 in the prime factorization, well, that doesn't do anything here because there's no 7's in this prime factorization. So that's one thing. The second thing is the numbers that are prime also won't work, except of course 5 and 2, which we want here, because we can just forget about the primes from 20 down to 1 because they don't give us anything. It's just 1 and that number. So that makes things a little easier. Well, 20 here, I can make a whole bunch of tiny factorial trees. 20 is 2 times 10. 2. 10 is 2 times 5. And well, 19 is a prime, so 1 and 19 are its only factors, so I don't have to think about that. Well, 18 is even, so it has a multiple of 2. It has 2 in it. So I'm going to calculate 18. Well, 18 is 2 times 9, 2. And 9 is made of 3's, so I don't even have to finish this factorial tree, just 2. So, I mean, this is what I said about needing a whole lot of more space. 17 is prime. I don't have to write that. 16 has 2's in it. In fact, 16 is just 4 2's. To do the 4th, just to save space, I'm just going to write 4 2's. 1, 2, 3, 4 2's. I'm just going to sneak in a little 15 there, because 15 has 5 in it. It's 3 times 5. 3 doesn't matter, so it's just 5. Moving on to the second row, let's see, 14 has 2 in it. So 2 and 7. Circle 2 because that's what we want. 13 is prime, 12 is even, has a 2 in it. 2 times 6. 6 is 2 times 3. Circle 2, 3 doesn't matter. Let's see, 11 is prime, no need to think about that. 10 is even, has a 2 in it. Happens to have a 5 in it too. Can't really see that too. 2. Well, 9 is 3 times 3, so we're moving on to 8, 2 times 4. So we have to calculate that. 2 and 4. Wow, decreasing pretty fast. 4 is 2. 2. 2 times 2. Okay, third row. Let's see, 7's prime. 6 is 2 times 3. 2 times 3. 2 we need. 5 might seem like a prime, although, well, we do want 5, so I'm just gonna go ahead and circle 5. 4 is 2 times 2, we need that. 2, 2. 3, no need. 2, again, prime, yet we need it. Well, 1's nothing. I feel bad for little 1. So, okay, a lot of 2's and 5's. Well, let's see, count this carefully. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, let's see, 16, 17. So let's see, and let's see, 2 to the 17th. That's a whole lot of 2's. Now 5's. Well, 5, or 1, 2, 3, and 4 times 5 to the 4th, and now we're virtually done because, well, the greatest common exponent here, we have 17 2's, yet 11 of those 2's don't matter because the greatest common exponent here is just 2 to the 6th, and we have 5 to the 4th and 5 to the 5th. Well, the greatest common exponent there is 4, so 5 to the 4th. Well, 2 to the 6th times 5 to the 5th is 20,000. We're missing 1 5, so 20,000 divided by 5, which I have no space to write this, is 40,000.